So now that we've talked about what a concurrent collection is, kind of at a high level, let's go dive down and look at a couple of examples of concurrent collections. And we'll focus here on concurrent hash map and on blocking queues. So what is a concurrent hash map? Well, as the name implies, it's a hash map that provides concurrent operations on the key value pairs in the map. And it has a combination of both object-oriented and functional programming interfaces, and we'll see some examples of both. And the key thing that makes concurrent hash map cool is the fact that it's optimized for concurrent programs. A hash map, as you undoubtedly remember from knowing about hash maps, it provides something called an associative array, where you have a value that is associated with a key in the map. A map also cannot contain duplicate keys, and therefore each key maps to at most one value. There's no duplicates in a hash map. This is kind of what it looks like under the hood. You have a hash table, which is this thing here, which, as you probably recall, hopefully from your data structures class, is an array from 0 to some number minus 1. And at the array is an array of pointers to something, and we'll see that concurrent hash maps are pretty clever. They're either pointers to linked lists, or if the linked lists start getting long, they become pointers to binary trees, balanced binary trees, which is pretty cool. We'll talk more about that in a second. If someone gives the hash map a key, that gets hashed with a hash function, which is something that will sort of try to, as much as possible, randomly put the keys into the appropriate location into the hash table array that's used here to access the buckets that happen to hash to the same location. Hopefully everybody remembers their hash table logic from data structures course. Here's a very simple example. If you have a concurrent hash map, you can treat it as a map or a concurrent map. You can initialize the map, and then we go ahead and put an item into the map, and that would then, hash it somewhere and stick it in there, some key value pair in the map. And when someone goes to look it up, then they'll get back the value that was put there. So if they look up key 1 after it's been put, then they should get back 42 as the value. Okay. So if you put in thread T1, then that has to, quote, happen before the get in thread 2. And all that really means is that you don't want to get half the results. You don't want to come down here and put the key in the map, but the 42 hasn't quite shown up yet. And then when this guy goes and reads key 1, he gets back a null or something like that, or some other value. So that's all it means by happens before. It just says that happening occurs such that the entire object is updated in the map, so that when someone goes to read key 1, either they get nothing because it hasn't happened yet, because it's not in the map, or they get back the appropriate value 42. And we'll talk more about happens before relationships later. If you have 2 items that are put into the map that happen to hash to the same location, even though they have different key values, then that's resolved by sticking 1 at the end in the linked list. So if for some reason key 2 was also to hash at this location, then it would just get stuck here in the linked list. In later versions of Java, and Java 8 and then beyond, the linked list is replaced automatically by a binary tree when the number of elements in a bucket reaches a certain threshold. So after you get a bunch of things hashing, then they go ahead and put a balanced binary tree. And this, of course, means that the worst case behavior of hashing becomes essentially log n at the worst. One of the downsides with traditional forms of hashing, if you just use linked lists, then conceivably you could have essentially order n worst case execution time. If everything happened to hash to the same location, then you'd end up with linear search basically to resolve the items. By doing this optimization, then even in the worst case, it ends up being log n time, which means, of course, if you were to insert n items into a hash map, they would end up going in there in no more than n log n time. Yeah. What's that? It's a balanced binary tree. So the question was, if this was not a balanced binary tree, then we could still be back to the same problem before if it all ends up, by some quirky twist of the adversary doing evil things to your data structures at the worst possible time with the worst possible input data, you'd end up with linear search again. But yes, these are balanced binary trees. Probably red-black trees, that seems to be the balanced binary tree of choice in Java. But it could be something else, AVL trees or 2-3 trees or whatever. But the point is it's balanced. Okay, so one of the things that concurrent hash maps do is they're optimized for multi-core CPUs. And if you read this article, it talks at length about what cool things they did to implement the concurrent hash map. It's really neat. I'm going to summarize some of the high points in the article here. So the first thing that the concurrent hash map does that's really cool is rather than just having a single lock for everything, which is the way synchronized maps work, this will have a group of locks, up to 16 in all, each guarding a subset of the hash table. And they're called segment locks. So let's say you had a hash table that was of size, I don't know, 160. Then, if you had 16 locks in there, they would each guard 10 elements in the hash table. So that way, if you hash and multiple things are hashing to different segments of the table guarded by different segment locks, you'll end up not having to worry about contention because they'll be locking different locks. So that's one of the big improvements over a synchronized map. There are human-known uses of this. If you've ever gone to an outdoor festival, remember back in the days when we used to have festivals and we could do things as groups, like a week ago. Here we have a bunch of porta potties, and this is exactly the concept here, except you don't have a balanced binary tree of people waiting in line. But basically, you partition yourself so that multiple people can use the restroom facilities without having everybody in one big line. So that's kind of the same idea. This method is cool because, so in addition to segment locks, it also allows read-write operations to proceed with minimal locking. So all read operations, even if you have everything hashed to the same segment, controlled by the same segment lock, read operations like a take, for example, will all run concurrently. And that's because the contents of the cells that make up the linked list or the trees are immutable, which means once they're created, they never change. The data fields can change, but the actual structure of whatever you hash to, be it a linked list or a tree, won't change. So as a result, there's no need to lock when you're doing reads. So all the take operations can run totally in parallel, which is really cool. Reads and writes are concurrent if they happen to occur on different lists or trees. So even if they're controlled by the same segment lock, if they're at different places within that, they can run in parallel too. So that's good. The only place you have to lock at all is if you do write operations to things that are in the same location. So if they hash to the same location and you're doing writes, then there may be a little bit of locking. But if you're doing reads on the same location, again, you can be clever about optimizing that stuff. And so this talks about what they do. They atomically add items to the head of the list. If you're removing something from the list, they set the flag, they set the field to null, and then they skip the cell. So again, really clever optimization techniques, and they eventually garbage collect these things. So long and the short of it is it's very, very optimized for concurrent read and write operations, unlike a synchronized map, which has one lock and doesn't have all these other clever optimizations put into that. One of the things that you have to remember about a concurrent hash map, and this will actually show up in the next programming assignment, next part of assignment number 3, is that you never fully lock the entire map. So if you're doing, inserts and removes and finds, any individual operation is synchronized and will be correct, but the whole map is never locked. And that is good because it means it's super fast, but it also means there's some subtleties you have to be aware of because of the fact the entire map is never locked. Also, if you can make changes to this and you won't get the dreaded concurrent modification exception. If you try to modify a normal lock, a normal hash map like a synchronized map or a regular map concurrently, you'll get the concurrent modification exception thrown. One of the quirks about the fact of the implementation, because the whole map isn't locked, is changes may not be available immediately. They may not be visible immediately. They will be eventually visible, but it's called weak memory ordering and weak visibility. That's not usually a big deal, but just be aware of the fact that things won't show up right away because there's no single lock that pushes out all the changes to all the threads the way it would if you used a synchronized lock. For your purposes, that really doesn't matter, but you have to be a little careful in other use cases. So, in contrast, a synchronized map only uses a single lock. There's just one instead of being up to 16 of them, and that can cause contention. So that's kind of like everybody waiting in line for one restroom, right? So you have a big line that's slow. So that's kind of the difference there. So as a result, the concurrent approaches are much faster, and if you want to demonstrate this yourself, there's this EX19 example in my GitHub repository, and it's pretty cool because it has this little test it runs, and one of the tests uses a concurrent hash map. Basically what it's doing is and I think we're going to look at this shortly, it basically goes out and checks to see if numbers are prime, kind of like some other examples we've looked at, and it has a concurrent hash map where all the different threads can run concurrently and look up and insert into the map concurrently. Then there's also another variant where things are synchronized, and you can see the performance difference. Look at this. So if you test the performance of these things, the performance to do, let's say you're putting 100 items or 100,000 items or whatever it is into this hash map. The concurrent hash map executes in 351 milliseconds, whereas the synchronized hash map executes in 1409 milliseconds. So it's basically, almost 4 times slower to do the synchronized map. And when you look at the code, which we'll look at, it's obvious why that's the case because it's a quad-core CPU, and we're running it at full tilt. So we have 4 threads running on those 4 cores doing put and get operations or put and take operations on the maps. And this one is much, much faster because there's very little contention, whereas this one is much, much slower because there's a lot more contention. And we'll look at that code here shortly. The other cool thing that the concurrent hash maps provide are these so-called atomic get and maybe set operations. So I like to call them, basically atomic check then act operations. And we've seen some examples of this before, things like compute if absent or put if absent, which conditionally do stuff depending on whether you're the first one in or not. And we'll take a look at this. This is really cool, very, very optimized. Don't have to do a lot of work yourself to make these things work like that. So here's some examples of these atomic get and maybe set methods. So one is compute if absent. We've talked about this before. So what the semantics of this operation are, try to put the key, or try to look up the key in the map. If the key already has a value, return the key. If the key does not have a value, call this mapping function, which takes the key and computes a value and puts that into the map. And that is equivalent to this code down here. This is the equivalent code. This is not how it actually works under the hood semantically, but it's logically the same. So this code here is like, come in, look up in the map, get the value. If the value is non-null, return the value. If the value is null, then go ahead and compute the value by applying the mapping function to the key. If the value is not null, then go ahead and put the item into the map. And so this is basically the semantics of that call logically. Here's another one. This is put if absent. If the key isn't already associated with a value, associate it with that value. So what this says is if there is nothing in the map with that value, go ahead and put it in there. Otherwise, don't do anything. If it's not absent, just return the value. So here's what it looks like. You go ahead and look up the key in the map. If you find it null, put the key in the map. and return what you put in there, otherwise return what was already there. There's also some other interesting operations, and these are important to remember for assignment 3B. I'll probably remind you about that when we do that assignment in a bit, but there's a really cool method called replace, and there's actually a couple of variants. There's the 2-parameter version and the 3-parameter version. Let's talk about the 2-parameter version first. This version will replace an entry for a key only if it's mapped to a current value, or to some value that you designate. So replace key with value will update the key with the value only if it has the current key. So that's logically like if the key is in the map, then put the value with the key and return the value, otherwise return the old value, otherwise return null. Here's the interesting one. This is a really cool method, and this is going to look familiar to you because this is basically the atomic check then act or check and set operation that you've seen with compare and swap, if you recall compare and swap from earlier discussions about Java atomics. This is sort of the collections version of atomic compare and swap. So what it's going to do is MapReplace says if the key is in the map and it has the old value, replace the old value with the new value. And remember this method. And it returns true if it made the swap and false otherwise. So here's kind of what this corresponds to. Again, this isn't the implementation, but it's the semantics if done atomically. If the map contains the key and the key's value equals old value, then replace the old value with the new value and return true. Otherwise, don't do anything. And you'll need to use this for assignment 3B because there's some things you'll need to do when you're implementing the Palantir manager for assignment 3B that uses a concurrent map. And you'll see you have to be real clever about how you do this. And the way why this is useful is it allows you to be able to get around any other synchronizer in order to update the map. So currently, if you think back what we've done for assignment 1B and 2B, in assignment 1B, we used a spin lock or some variant of a spin lock to guard access to the hash map. In assignment 2B, we used a reentrant lock to guard access to the hash map, both of which would lock the entire map. For assignment 3B, you're going to use a concurrent hash map, and there is no need for other locks. So you'll see how that works, and it uses the replace operation in this compare and swap-like way to do it. It's pretty cool. All right, so that was concurrent hash map, and that's really what you need to know for assignment 3B, at least part of it. Let's talk briefly about blocking queues. So a blocking queue is a queue that supports operations with certain properties. You can kind of see the overall class relationships here. So we've got blocking queue as an interface, which basically inherits from collection, iterable, and queue. So it's got quite a number of methods in it. And then blocking queue then serves as the interface for other interesting mechanisms, other interesting classes, like array blocking queue, link blocking queue, priority blocking queue. These are all examples of blocking queues in one way or another. And one of the things that a blocking queue does that a normal queue doesn't do is it'll allow a program to be able to wait for the queue to become not empty when you retrieve elements from it. So if there's nothing in the queue, then it'll block when you try to take an element out of it, which is what a blocking queue does. And then it also, conversely, allows a calling thread. So this is what works for a consumer thread. For a producer thread, it also allows the producer thread to wait until the queue is not empty. It's not full, rather. So if the queue is full and you try to put something into a full queue, then it'll block until the queue is not full. Just like if you try to take something out of an empty queue, it'll block until the queue is not empty. So basically, it allows you to block around the boundaries of the queue being either empty or full. There's a couple different variants you have here. If you try to add to a full queue or you try to remove from an empty queue, you can either wait indefinitely for the queue to become not empty or not full, or you can also put timeouts. And you can say, I'll wait up to a minute for this queue to be not empty, or wait up to a minute for this queue to be not full. but you won't wait indefinitely for the queue to be not empty or not full. So you can bound the amount of time, and you can also basically poll, which means if it's not currently to your liking, just return right away with a null. So those are ways of bounding the amount of time that you wait for something to be not empty or not full. The most common way this is done is by using various Java synchronizers like reentrant locks and condition objects, as we've talked about before. In fact, if you go back and watch those videos on reentrant lock and condition object, you'll see we showed how to implement the array blocking queue using reentrant lock and a pair of condition objects, and linked blocking queue is sort of along the same lines. It's more sophisticated, but it's kind of the same. So that's an overview of concurrent hash map and blocking queue, and the most common blocking queues you're likely to run across are array blocking queue and linked blocking queue. Okay.